Welcome back everyone. In this lecture, as I promised, we will see the proof of the dimension theorem. So, let me recall the statement. So, let G be a finite group as always, and then we take rho to be irreducible representations of G with, let us say, the character chi. So, then the dimension theorem asserts that the degree of chi actually divides the cardinality of G. So, this is indeed a very simple theorem to state, but this proof the proof of the theorem actually requires little bit of algebraic number theory. So, let me quickly actually go through some of the important results from algebraic number theory, and whatever results that we required in order to prove this theorem, those results I will prove it very explicitly, but other than that remaining fact I am not going to prove. Okay, so here is a quick tour in number theory. So, first let us actually begin with the definition of algebraic numbers. I hope all of you might be knowing this. So, let me just anyway recall it. So, here is the definition of algebraic number. So, we say a complex number alpha in C. So, it is called an algebraic number if it is the root of a polynomial with integer coefficients. So, this is called an algebraic number if there exists a polynomial p x with integral coefficients. So, this is the polynomial ring where polynomials whose coefficients are integers, and you have this p of x such that the p of alpha is indeed 0. So, we want some non-zero polynomial such that p of alpha is 0. So, we denote this q bar by the set of all algebraic numbers, the set of all algebraic numbers, and it is a fact from basic field theory that this q bar indeed form a field. Okay. This is a subset of C and this is a subfield of C. So, note that q is there and q is sitting inside q bar and which is sitting inside complex numbers. So, if you compare the cardinalities, so the complex numbers they are uncountable. So, this set is uncountable and it is not very hard to prove this q bar is indeed countable and it is countably infinite set. So, this can be easily observed from the fact that if the polynomial ring over integers, this is indeed a countable set. So, that means most of the complex numbers they are going to be algebraic, not algebraic. So, when we actually look at these non-algebraic numbers, so they are indeed very much dense inside complex numbers. So, we call them transcendental numbers. Okay. So, the elements of the C difference q bar they are called transcendental numbers. And it is actually indeed a very difficult problem to decide whether given number is complex number is transcendental or not. So, for example, E and pi they are transcendental, but it is indeed very difficult to prove these facts, actually very difficult to prove. But like I said, we are not going to get into this general field theory things. So, what we are interested in, we want to prove that uh, the degree of irreducible representation that indeed actually divides the cardinality of G. So, one of the main strategies in number theory to prove given number actually divides the other number. So, that means the degree of chi divides the cardinality of G. So, what we will actually do, so we actually prove that the cardinality of G divided by the degree of chi, this is indeed algebraic integer. So, to prove this is an integer, we will observe that it is enough to prove this cardinality of G divided by degree of chi, this is indeed an algebraic integer. And a rational number which is an algebraic integer must be an integer. So, that is the fact we are going to use, and most of the times it will be actually easy to prove something is an algebraic integer. Easy in the sense technically proving something an integer is going to be difficult, but proving something an algebraic integer is somewhat easier. Okay, so let us actually see what is an algebraic integer. So, algebraic integer is an algebraic number, but the polynomial that actually it satisfies over integers, that should be monic polynomial. So, here is the definition of algebraic integer. So, given alpha in q bar, so is said to be, so maybe we will take it from complex numbers only, is said to be algebraic integer if there exists p of x from this zx, the set of polynomials over integers, such that, so this p of x is indeed monic. So, that means you can write it as some x power k plus a k minus 1 x power k minus 1 plus etcetera plus a naught, and we want this alpha to be a root of this polynomial p of alpha equal to 0. So, basically if there exists a monic polynomial with integral coefficients such that p of alpha equal to 0, then we say this alpha is an algebraic integer. So, let us denote this a by the set of algebraic integers. Indeed, what one can prove that this form a subring of complex numbers. So, this is the most important result. Okay. So, maybe let me state it as a theorem. So, this will be required for us. So, the set A, it is a subring of complex numbers. So, that means addition of two algebraic integer is an algebraic integer and product of two algebraic integer is an algebraic integer. So, not only that there is this conjugate map from C to C. So, the set of algebraic integers that will be invariant under the conjugate map. So, in other words, whenever alpha is in A, that would imply the conjugate of alpha, complex conjugate, that is also again an algebraic integer. So, these are the two important facts about algebraic integers. So, let us first see some examples of algebraic integers. It is not difficult to see that all integers are algebraic integers. So, one can take for example x minus alpha as a polynomial p of x if x is in G, and similar to that we can also take these eigenvalues coming from integral matrices. So, those things also going to be algebraic integers. So, let us take A to be Aij, so which is a matrix, let us say T by T matrix over integers. Then look at the roots of the characteristic polynomial of this A, which is the characteristic polynomial which is defined by P A of x equal to determinant of x times identity minus a, and these are the eigenvalues of this integral matrix A, and it is clear that since these are all roots of a monic integral polynomial, so they are all part of this set of algebraic integers. So, this is something that we are going to use it very much, and it is also clear that any nth roots of unity, that is going to be again algebraic integer. So, any nth roots of unity, so that is again algebraic integer, because it satisfies the equation x power m minus 1. So, these are all some well known classes of algebraic integers. So, we are going to make use of them in order to prove our result. Okay. So, to prove this theorem, let us make the following observations. So, we need a couple of small lemmas. So, here is the first lemma. A rational number, that is an algebraic integer if and only if that must be an integer. So, that means whenever I take q intersection with a, that is going to be exactly g. So, it is clear that g is subset of q intersection a. So, this is very clear. Now, we need to prove the other way. So, let alpha be an element in q intersection a, and let us say p of x is the monic polynomial that it satisfies. So, which is given by some x power k plus etcetera a1 x plus a naught, and this is the monic polynomial that actually alpha satisfies. So, now you can see that you can write this alpha as a by b with GCD of a comma b to be 1. So, now if you substitute this in the equation p of alpha equal to 0, we can see that we get exactly a by b power k plus some a k minus 1 a by b power k minus 1 plus etcetera plus a naught equal to 0. So, note that all a naught etcetera a k minus 1, they are all integers. So, now if we cancel out the denominator by multiplying by b power k, we get a power k plus b a k minus 1 a power k minus 1 plus etcetera plus a 1 p power k minus 1 a plus a naught b power k equal to 0. So, now look at the term that is here. So, this term has b in it everywhere. So, this is indeed multiple of b. So, that means b divides minus a power k. But since GCD of a and b are 1, so this would never happen unless b is plus or minus 1, and this would imply that b is exactly plus or minus 1. So, what we can do, we can choose a prime divisor. If b is not plus or minus 1, choose a prime factor of b, then that prime factor divides a power k, that would imply that that prime factor must divide a. So, that will tell you that GCD of a b is at least that p, prime factor p. So, that is a contradiction. So, because of that we can get that b is plus or minus 1. So, that would imply that this alpha is an integer. So, this is somewhat very simple check that actually says whenever rational number is an algebraic integer, that must be an integer. Okay. So, we are going to use all these things. We can easily see that the cardinality of g divided by the degree of chi, this is indeed a rational number. So, if we prove it is an algebraic integer, then from previous lemma we will get that cardinality of g divided by degree of chi is an integer. So, this is the strategy that we are going to follow. but this is, like I said, bit involved. It is not that easy to prove, it requires some work. So, let us see how one can prove this. Okay, so we are indeed going to characterize algebraic integers in some different way. Okay, so if we ask me, so where the algebraic integers actually naturally appearing, so that actually directly comes from the character values. So recall that. So let me make this observation. So let us start with the representation row, let us say from G to some GL MC. So now let us say chi is the corresponding character, the character of row. So then what happens? So we can take n to be the cardinality of G. So let us fix this. Whenever we look at the value of this chi of G, so this is nothing but the trace of rho G. So now this is nothing but the sum of the eigenvalues of rho G. So this is exactly the sum of the eigenvalues, let us call it lambda 1 etcetera lambda m of rho G. Of course, we are counting with multiplicity. So why this is true? So note that n is being the order of G, it is clear that G power n must be identity. So this comes from the Lagrange's theorem. So since G power n is identity, by applying rho we see that rho of G also has this exponent n. So that means R of rho of G divides n. So this implies that rho of G satisfies this polynomial x power n minus 1. Since x power n minus 1 they all have distinct roots, all the roots are nth roots of unity. So that implies that rho of G, the minimal polynomial of rho of G divides this x power n minus 1. So the minimal polynomial of rho of G divides x power n minus 1. So that would imply that all eigenvalues of rho of G, so they belongs to this nth roots of unity. So not only that, the rho of G must be diagonalizable operator. So with respect to some basis, the matrix of rho of G is going to look like this lambda 1 etcetera lambda m. So that means the trace is going to be the sum of the eigenvalues lambda 1 etcetera lambda m of this rho of G. Now since all these lambda i's, they are nothing but nth roots of unity. So you can easily see that the chi G, which is the sum lambda 1 plus etcetera lambda m. So this must be an algebraic integer, because all nth roots of unity must be algebraic integer. So since the set of algebraic integers form a subring, so the sum is also going to be algebraic integer. So this indeed motivates us to actually look for this algebraic integers. Okay, this is how we are getting the connections with algebraic integers. So note that chi of 1, when you evaluate it on 1, so this is, we already know nothing but the dimension of the representation, which is exactly the degree of chi. So somewhere we are actually getting the connections between the algebraic integers and the character values. Okay. So that is how the connections made first. So that is why we are interested in understanding the algebraic integers. Okay. So let us actually make some characterizations of algebraic integers, and that characterization is actually going to tell us immediately that the set of algebraic integers form a subring. Okay, so let us prove this characterization. Let us call it lemma 2. We fix some y in complex numbers. So, then so actually if you think about it, these ideas are very closer to like whatever you have seen in Galois theory. So, Galois theory means looking at the extensions of given field. So, here since we are working with algebraic integers, so we have the following characterization in terms of these integral matrices. So, let us make this. This is indeed a very nice observation which will tell immediately that the set of algebraic integers they form a subring. So, we have that this given complex number is an algebraic integer if and only if. So, there exists this y 1 etcetera y t, of course, some t greater than or equal to 1 and this y 1 etcetera y t, not all of them are 0. So, that means this is not 0 vector such that we have the following equations. So, that means, so when you take the product y y i, so this is indeed an integral linear combination of y i. So, that is the important constraint. So, when we have y is an algebraic integer. So, you have this a I j, y j, j range from 1 to t, and with the thing that this a I j they comes from this t by t integral matrix, and these y i's they could be some complex numbers. So, that is not important actually. So, only important thing is they are not all of them 0. So, what this means? This means y y I is an integral linear combination of these y i's. So, this is what this equation star means. Okay. So, whenever you have this y 1 etcetera y t, not all of them 0, such that y y I is nothing but integral linear combination of y j's. So, then you have actually y an algebraic integer. So, this is actually somewhat practical way of checking given given complex number whether it is an algebraic integer or not. Okay. So, let us actually look at the proof. So, the forward direction is very simple. So, let us pick up this polynomial p of x, monic polynomial such that p of y is 0. So, let us write down this p of x as, so this is monic. So, as x power t plus a t minus 1, x power t minus 1 plus etcetera plus a naught. So, now given that p of y is 0, you can see that you have this equation that y power t plus a t minus 1, y power t minus 1 plus etcetera plus a naught equal to 0. So, now what we can do? We can simply set this y I to be y power I minus 1 for all I between 1 to, so yeah, we can take it to be 1 to t. So, we just simply set this y I. So, then it is immediate that when you actually multiply y with y I for I between 1 and t minus 1, all it is going to do is increase the power. So, y y I is going to be y times y power I minus 1. So, which is going to give you exactly y power I. So, which is exactly equal to y I plus 1 by our setup. So, this is true for all I between 1 to t minus 1. Now, what happens when I equal to t? So, then we get y y t equal to y times y power t minus 1, which is exactly equal to y power t. So, now we can rewrite y power t in terms of all these things. So, then you can see that y power t is exactly minus a naught minus a 1 y minus etcetera minus a t minus 1 y power t minus 1. So, now you can see that y etcetera y power t minus 1 they are nothing but some y i's. So, that means y y t is linear combination of y i's. So, that actually proves the forward direction. So, the forward direction is very simple, but for the converse part we will use that all the eigenvalues of given integral matrix they must be algebraic integer. So, given this y 1 etcetera y t they are going to actually produce indeed a matrix A and an eigenvector y. So, assume that y 1 y t are as in the statement of the lemma. So, that means this y 1 etcetera y t they are all not 0. So, that means they are non-zero vector in C t such that we have this following equation such that y y I is nothing but summation a I j y j j range from 1 to t. So, this equation is true. So, now what we can do, we can just simply set capital A to be a I j and then capital Y to be the vector y 1 etcetera y t, y 1 etcetera y t, and this star then read as follows, then star becomes a y the ith column is exactly given by summation a I j y j j range from 1 to t. Sorry, the ith entry a y is, so A is t by t matrix and this is exactly t by 1 matrix. So, a y is exactly t by 1 matrix. So, the ith entry of the row, so that is going to be exactly given by this summation a I j y j, which is by star is exactly y y I. So, that means this is exactly y times the ith entry of this vector y. So, this simply rewritten as follows, a y is given by y y. So, that means capital Y is an eigenvector for the matrix capital A and small y is the eigenvalue. Corresponding to capital Y. So, that means this small y is nothing but an eigenvalue of this capital A. So, it is a root of this determinant x I minus a. So, but we have already seen that determinant of x I minus a is a monic integral polynomial because a comes from, so a indeed comes from m t of g, all the entries of a are integral integers. So, in particularly this y is a root of monic polynomial with the integer entries. So, that would imply that y is indeed an element of A. So, this indeed proves that so we have this characterization of these algebraic numbers. So, now it is not hard to prove our theorem that A forms a subring of C and given alpha the conjugate of alpha is also there in A. Okay, let us prove the main theorem that this A is a subring of C and whenever alpha is in A implies alpha bar is in A. So, the proof of the second statement is very simple. If we take this P of alpha is 0, where p of x is the monic polynomial that we have chosen, such that this p of alpha 0, then that would imply that p of alpha bar is also 0, because p of alpha bar is same as p of alpha bar, because all the coefficients are integers, they are invariant under taking conjugates. So, that would imply that p of alpha bar is same as p of alpha bar. So, this would imply that alpha bar is indeed an algebraic integer. Okay. So, let us prove indeed the first statement, which is little challenging. So, we just assume that y and y dash are given elements from the set A. So, we want to claim that both the addition and the multiplication both are there in set A. So, let us use the characterization. So, we know that given y, so there exists this y 1 etcetera y t and then y 1 dash etcetera y s dash, they satisfy some conditions. So, let us write it them. So, given y, we have this y 1 etcetera y t, not all of them 0, such that this y y I is linear combination of y j's. So, this is exactly integral linear combination, that is the most important thing. So, this is true for each I. And similarly, since y dash is in A, there exists y 1 dash etcetera y s dash, again not all of them are 0, such that this y dash y k dash is again given by some linear combination of y j dash. Let us call the entries b k j. So, where as we noticed a I j's are all integers. So, that is important. Again similarly here these b k j's are all integers. So, these two things are there, that actually comes from the fact that y dash they are algebraic integers. Now, combining these y i's and y j dash, so we are supposed to get actually some elements for this y plus y dash. But if you think about it, it is not very hard to actually come up with them. So, it is easy to see that when you take y plus y dash and then y I y k dash. So, this is going to be linear combination of y j y l dash. Indeed, what happens? So, this is exactly equal to y y I y k dash plus y dash y k dash y I. So, now note that this can be replaced and again this can be replaced using this 1 and 2. So, now this is using 1 and this is using 2, we replace. So, then what we get, this is exactly equal to summation a I j y j y k dash and then this is summation b k j y j dash y I. So, now see that this is exactly equal to an integral linear combination of y j y l dash. So, that means this term y plus y dash actually satisfy the required condition that we had it in the lemma. So, that implies that y plus y dash, that is indeed element of A. Similarly, we can also prove that the product also satisfy the same condition, that is because if you take y dash and y I y k dash. So, this you can read it as y I times y dash y k dash. So, now note that so this is an integral linear combination of y j, this is integral linear combination of y l dash. So, that means the product is going to be an integral linear combination of again y j y l dash. So, that proves that y dash satisfies again the criterion in the lemma. So, this must be an algebraic integer. So, both y plus y dash and y dash, they are algebraic integers. So, that actually proves that the set of algebraic integers that will form a subring of complex numbers. So, we will use all these observations in order to prove the dimension theorem. I will do it in the next class. Thank you.